Okay, so we're going to talk about the central limit theorem here, but I want to do a quick recap. What we're doing is we're thinking about what would happen if I repeatedly sampled over and over again, what would my distribution of means look like? And we said the middle of that distribution of means would be somewhere around mu, the truth, the population parameter, right? That's mu. And we said that there would be some sort of spread to those means. We wouldn't get the same mean every time. I had a student say, why? Because I suck at science and it's not replicable? No, it's because you get a different mean each time. It's random. So the spread of these is described by the SEM. And the SEM is what is the distribution in the population divided by the square root of the sample size. Now, the reason why we're doing this is that in the next few weeks, we're going to do this really important statistical thing called estimation. An estimation is when you take one sample, like you do in real life. You take a sample, you do a study, and you say, what does that study tell me about the truth? But in order for us to understand that process, we have to go through this part. And this part is really driven by the standard error of the mean, which describes the spread of the sampling distribution of means. And when we talk about distributions, we always talk about three things. Where's the central tendency, the middle? What's the spread? And remember, what's the shape? And in this video, I'm going to show you a little bit about the shape. And this is known as the central limit theorem. The central limit theorem says that no matter what the shape is of the individual values, that when you look at the distribution of means, it will be normal. And this is going to be really important when we build up this idea of estimation and of hypothesis testing, because we know special stuff about the normal distribution. We know most, almost all, and seriously, dude, almost all the points are within these certain values. We know how to reference individual points in a normal distribution. So the fact that this is normal is going to allow us to do a lot of different things. Now, I want to show you how central limit theorem works. This is another great applet that I have. This comes from the online stat book. I want you to take a look at this, and you can play around with it on yourself too. Notice that at the top of the screen, we have a distribution of individual people. The mean is 16, and the standard deviation is 5. And what I can do with this applet is I can take a sample of 25 people out of that population, and it will calculate the mean of that sample, the X bar, and we get a value. Now, that's how we would normally do it in real life. And we would say, how close does that approximate or estimate the truth? But for this, let's do this again. Let's calculate another mean. Remember, all these people are being selected randomly. And then let's see what mean we get. So there's our n equals 25, and we get a different mean. But because we suck at science? No, because it's random. So we can do this again and again. Now imagine if you had all the time and all the money in the world, what would you do with your life? Travel the world, cure malaria, write the great American novel. You could spend your life sampling over and over and over again. There's a button under that says 100,000. And I'm going to press that button. And it's going to do exactly what we just did 100,000 times. Now, take a look at that. That is the sampling distribution of the means for a sample size of 25. And notice a few things. What's the shape? Normally distributed. Where's the central tendency? Well, you can see it to the left. It's 16. And then what is the spread? Well, remember what spread is. Standard error of the mean. It's sigma, which if you go up to the top, sigma here is 5, divided by the square root of n. N here is 25. 5 divided by 5 is 1. So look at that standard deviation. It's 1. Oh, that's really neat, Tybor. It's lucky that it just happened up that way. Well, we can do this. I can take this distribution and I can change it. I can make it a little more like this. 100,000. And look how this distribution is normal. This is the idea of the central limit theorem, is that no matter what the underlying distribution looks like, let's do a really weird distribution. This would be known as a bimodal distribution. When I take a sample, sample means are normally distributed. And this stresses that the central limit theorem says no matter what the distribution of individual people are, that top black histogram is, the distribution of means, that blue one, will be normally distributed. There's a couple more slides that just show you this in extreme values. Here are a couple examples of, look at that top right corner here. This is a weird distribution. That's definitely not normal. It's like this. But if we take samples of size 32 and calculate the mean each time, is normal. Check this out. Here's a distribution, not normal. Samples of size 30, normal. This one, not normal. Normal, not normal, 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 normal. And so this is the idea of central limit theorem, which says the distribution of sample means, if you have a big enough sample, will be normal regardless of what the individuals in the population look like. We're going to use this. This will be really important when we actually use these fundamentals to do some fun stuff. And the first thing we're going to do is this idea of estimation. Estimation is, let's take a sample, calculate a number, and say, what does that tell us about the truth? What does it tell us about the truth? If we take a sample and the average is this number of calories that the average person eats, where's the truth? Is the truth going to be exactly this? No, probably not. But we can take this and put some bounds or some interval or some sort of fudge factor around it and say we think the truth is somewhere between this. This is the idea of confidence intervals and trying to estimate where the population parameter is. And we will save that for next week. All right, watch this one again. And if you don't understand this one, watch the previous one again. Drop a like, subscribe to my YouTube channel. Thank you very much.